I will be showing you how this nanoparticle work. So I'm going to show you how we can test which among these particles can work better. So we compare our zinc, we compare the copper and then the normal purpurine, so we know which one can work better. Okay, so what I'm going to do now is okay, can you see my screen? Can you see my screen?
It's not up yet.
Okay, you will see it.
Not sure.
Sure.
Yes.
You will see it. In case you see it, let me know. Have you seen
You
it?
can see it now.
All right.
But
So let me change the name. Let me change the names that.
we can see your document.
All right. So let me change their names in my notepad so that it will. Let me save the structural name. All right. Okay. I want to change the structural names. So I'll be using a software called Pires. Now this Pires is a 3-in-1 software. The Pires is
Okay, spell the Pires. P-Y-R-O what?
Pyrs. Pyrs.
Okay.
So it's a 3-in-1 software. I use it for drug discovery and synthesis. So it has autodoc, it has autodoc vina, and it has open babel. Don't worry, when we come for the advanced training, I will expose you to that more. So, but I want to see how this compound can work against a disease. We want to see which one will be effective against a disease. So I want to work on hypertension, for instance. Let me look at a disease. I'm coming. Let me open up a okay, let me just use anyone. Okay, now this is the software. This is the Pires. This is actually the Pires, and I want to see which one will be more effective with my nanoparticle be more effective than the ordinary particle against hypertension. So I want to see how they can treat hypertension. So what I'm going to do is that I'm going to get my hypertension target. I will get the target of hypertension. I just want to show you. Coming. I want to pick up the target for hypertension. Okay, so I'm going to use this. So what is here now is one of the targets responsible for hypertension. I want to load it in. So this structure you are seeing here is a structure for angiotensin converting enzyme. Is one of the enzymes in the body that is responsible for hypertension. So we want to see the ability of the three compounds I have modeled, the ability to reduce or induce the ability to reduce this hypertension in the body. So we will know which one can serve as a better drug, right? So I'm going to, what I'm doing now is I am bringing in my hypertension ACE. So I will close it and I'm going to reopen it. It may take you a little time, but don't bother. You will see how that will work. It may take us a little time, but the idea today is for you to be able to model a nanoparticle. Then I think I'll give you 5 meters as assignment. This assignment I'll give you now might be heavy, but I'll make it lighter for you, Sha. Okay, so let me bring in my compounds. Let me bring in those three compounds I have been able to model. I think I was able to model, where are they? Zinc. Good. So this is the zinc purpurine. That is it. Then let me bring in the copper. The copper purpurine. And then lastly, let me bring in the normal purpurine, the ordinary purpurine. Okay, so I'm going to remember that I have minimized the energy, but I'm still going to minimize the energy again. So I'm going to minimize all their energy to make sure that they have smaller energy, and then I will do a little conversion. So I'm converting the structure from SDF to another format. Right, that will just take us little time. Good. So what I'm doing right now is called molecular docking. In case some of you must have heard about molecular docking, that is what I'm doing. I want to see these 3 compounds, which one will have a better result on the hypertension. Maybe I pray that the nanoparticles should have a more better result than the hypertension. So I will allow each of them to interact. So right now what is happening now is that the zinc purpurine is running. If you can see my screen, it's showing running, meaning that the zinc purpurine that we just modeled is interacting with the hypertension target. Once it's done, this line will read up to 100. Once the zinc purpurine is done with the interaction, the copper purpurine will also interact, and the abnormal purpurine will also interact. at the end we know the one that has the highest binding energy. The highest binding energy, which means that one can easily work better. Okay. So we'll just give it a little time, but we can be doing other things. Let me give you aspirin, for instance. Why that is going? Let's come back. If I have aspirin, how will I identify the binding site of aspirin? So let's come back to our chem draw. Let's say we have aspirin. How will I identify the binding site? Because the major problem is your ability to identify the binding site. So on this, I want us to respond to this aspirin now. Look at this aspirin. How many binding cavity does it have to you? How many binding cavity are you seeing here?
Two.
Which one and which one?
Two.
Okay, two.
Is it two?
Oh, yeah, she's not asking.
The COOH.
Yes, the COOH.
No, I said the carbonyl now, like.
Okay, here.
Oh, yes. Are you sure?
We can pick
Yes.
this OH first.
Yes, that one. Yes, OH and CO.
I can pick this one. I can take this and this. So I can use both of them to form my metal complex. So that means what I'll just do is I need to make this shape. Let me change this shape so that if I'm drawing I'll just need to do something. I will bring this one back here. Take this one. I'm just changing it, but it does not change anything. I just want to align it in such a way that it will be good for me if I am. Oh, I begin to do rubbish. Okay. So I can pick. I cannot make it twice. So you can make it twice. You can make it twice. You can make it twice, and since it has two binding sites.
I'm sorry, Madam Henry.
Yes.
Sir Henry.
I can hear you.
Question.
Okay.
Why are we picking the other C double bond O? I was thinking we would just pick from the carboxylic acid only.
Okay. The reason is that
Can you hear me?
yeah, I can hear you. The reason why I will pick one from this part and the other carbonyl, the acetyl carbonyl, is because I want a good capping. I want every part, the two major functional groups, to take part in the bonding. So if I use only the carboxylic acid group in the bonding, the interaction may not be effective. Yes. So I need the two functional groups to take part in the bonding. Let the acetyl group and also let the carboxylic acid group take part in the bonding. But you can now do different kinds. You can develop the one with only your carboxylic acid, develop the one with the acetyl group and the carboxylic acid, then compare them to see which one is actually effective. The one that's effective is what you proceed to the lab. So the idea is I can do all the trial by error with my computer. So you can model with only the carboxylic acid, or you can model with one of the acetyl group and the carboxylic acid group, the OH, and try both of them. The one that gives you a better result, you go with that one. So okay, my zinc purpurine is done. It's the interaction between the zinc purpurine and the hypertension is done. We are now on the copper purpurine. When that is done, it will move to the ordinary purpurine. So let me come back to this man. You just have to turn it to the way that it will be favorable to you. I want to place it in a way that should I say opposite to the way that it will be favorable to me. Okay, I think this way will be better for me. Okay, so let me use another element. Let me say iron. I can use iron and then pick up your single bond here. I can draw here. I can draw here. I can now take this one to this place. Is actually trespassing. Okay. But then I have to reduce the number of carbon here so that it will balance. It will balance with the oxygen. So I have to reduce this so that it will balance. So I pick up one to my iron and another one to my iron. So what I just did, okay, excuse me, let me shift it. I don't want any intersection, so I'm coming. Let me just see how I can adjust this man. Let me shift this man so that it will not intercept. It will not intercept with the carbon. Good. All right. It's still passing through. I don't want it to intercept. Good. So this is what I wanted. So what I just did now is, this is a nanoparticle of aspirin with iron. You can decide to work with hexadentate, that is 6 with a coordination number of 6. But the most stable coordination number for metal complexes is 4. But some persons like working with 6. Then to be sure, when you are done with this and you have done your efficiency with any of your tools, you can now go to the lab and do your synthesis. You can use green synthesis, or you can use a sow-gel method, any of the synthetic method available. After you have done the synthesis, you now go for characterization to make sure that what you have synthesized is actually what you got. So let's just wait. The copper purpurine is done. Now is remaining the ordinary purpurine. So at the end, we'll see the results. Which one is more better than the other. So you can appreciate the knowledge of nanoparticle. If you have a question to ask, you can do well to bring it up.
Aga Henry,
Yeah.
thank you so much for the lecture, sir. But on the side of this, the side of this thyroids, yeah, I think I'm lost too.
No,
I
definitely
don't know,
you
like,
must be lost.
is it because maybe I don't have the software or
No,
what?
no, it's deep. It's not. I just want to use it to show you something. I just want to use it to show you something. Okay, it's done. Now look at these results. Look at this result.
But we can still have the knowledge.
Now look at these results. Can you see the screen? Look at these results.
Sure, we are seeing
Yes,
it.
we can.
Now, which of them has the best results? Which of them has the best results? Look at the binding affinity. What's the top?
So we're going to look at the binding affinity, right?
Yes, yes. Look at the binding affinity.
Minus 1.6.
And that is for who? For which of the compound?
Hmm?
Aga Henry, we've seen the
Copper.
binding activity, we've
Yes.
seen the mode and the other information, but how do all this information relate to the efficacy?
Okay. Okay, fine. The one that has the more negative.
I hope you understood my question.
Yes. The one that has the more negative binding affinity is more efficient. The one that has the more negative binding affinity is more efficient, more reactive. Remember, we are trying to explain last week about grease-free energy, enthalpy. The more negative your energy will be, the more efficient, the more reactive that molecule will be. So we now look at which of them have the highest binding affinity. That word binding means, each of them we are interacting with the protein, with the hypertension target. They were binding. So which of them has the highest binding affinity? So the ones that can bind more has the highest binding affinity. That means that one is more efficient.
Okay.
So that means that one is more efficient. Now, if you can see the screen, and you're seeing that copper has the highest, which is 11.6. Am I right? Minus 11.6. Zinc purpurine is the next, which is minus 11.5. Now, the normal purpurine is giving us minus 8.3. Can you compare their difference? Can you compare the difference?
Okay.
Your mind is not.
But I can still see the copper purpurine repeating again.
Yes, fine. Do you know why it's repeating? You are seeing under mode. You are seeing 0. Look, under the mode, Under the mode, you are seeing 0. Then you are seeing 1. You are seeing 2. You are seeing 3. We only pick the one that gave us 0. The mode of 0. That is what we pick. So we pick the result for the mode of 0. Okay, let me take this to Excel so that you understand more better.
Is there a particular reason why we take the mode 0?
Okay, Fine. I love the question. Now, look at the next column. The next column after mode, what are you seeing there? The next column after mode is what? RMSD, right? Are you seeing RMSD?
RMSD.
Yes.
Yeah.
That means root mean square standard
Sure,
deviation.
sure.
Yes.
Root mean square standard deviation. So anyone that has a 0 root mean square standard deviation is what we work with. That means that the deviation of the binding, the deviation of the ligand of those are compounds binding with the active site with our disease is 0. That means that the compound was able to fit in tight, to fit in firmly at the disease target. That is why we work with anyone that gives 0 RMSD. It means there was a 0 deviation. All the compounds that have 0, the value of the 0 is what we pick. If you look under the RMSD, you are seeing other values. So our interest will not be on those other values, but our interest will be on the ones that gave 0. The ones that gave 0 RMSD. Those ones that have 0 MSD have the best results. Okay, now take a look at copper. Copper under 0, you're having 11.6. But check copper again under 1. Under 1, what are you having? 11.0. So which one is more better? The 11.6. So we always pick values at 0 RMSD.
11.6.
Yes. So we pick values at 0 RMSD. Alright. You are using the idea to learn this thing. Although, if like you ask all the heaven and earth questions you want to ask, you will not still understand what is happening here. But you can ask. It's good.
It's only that we don't have the software.
No.
Now only because we don't get software.
No. You still need small learning.
If we have the software now, we can.
Okay, let me open this thing now. I just saved.
I have learned small now. If I should try it one time.
I just saved the result now in Excel. Let me open the result in Excel so that you see it more better in my Excel. So this is the result in Excel. This is the result in Excel. And this is our interest. So let me copy this to another sheet. So this is our interest. So now you can see clear, very clear. You can see it very clear that the copper poop ring is having a higher binding energy. I can take away this. We don't need them again. So this is what we can use to report if we are doing a project work. This is what we use to report. Now, let me now ask you a question. Is nanoparticles better than ordinary particles? From what we just did now.
Yes, from what we can see.
Yes.
From what we can see. Yeah.
So,
from what we can see, the nanoparticles have a better efficiency.
Good. So today you have gotten an idea that any molecule you are using to work, any substance you are using to do a research work, try to model it, try to use a nanoparticle. We are encouraging everybody to always make all their particles nano. Once you make any particle you are using to do a research, once you make it a nanoparticle, expect a better result, expect an efficient result, expect something better. Because let's say for instance you are using a catalyst to produce biodiesel. Maybe you are using a calcium oxide to produce biodiesel as a green catalyst. You can make it a nanoparticle. Yes, you can go to the lab, make that your catalyst a nanoparticle. So nanoscience have come to stay, and that is the essence why this is the first time I'm teaching students how to model a nanoparticle. You are always lucky. You are lucky that I'm always bringing something new to you. Something new to you. So is
You
a
have
good.
come, oh. You have come. Oh.
Yes, yes. I always say it that I always get something new each day. Something that is innovative. Imagine only ChemDraw. We have used only ChemDraw to do a lot of application. Now, how much more when you begin to learn others? Chemistry will be at your fingertips now. You will tell your HOD step down. I'm not the new chemistry lord. Eh, okay. Any question? Any question to ask? I've not heard our
So you have
boss,
gone out.
Idara. I've not heard your voice.
Oh,
You don't
I
sleep.
can hear you.
Eh?
Can you
he has not been able to log
can you hear
on.
me?
I can hear you.
Mr. Henry?
Yes.
Oga Henry Ade, sleep won't finish me for you.
I mean, I don't know. I want to ask a question
Yeah.
regarding this modeling of nanoparticles. Like,
Okay.
can you hear me?
I can hear you.
Are you there?
Yes, I can hear you.
Oh, all right. You said that advisable. So you said that it's advisable that all the compounds that we are working in that will convert them to nanoparticles. Like
Yes.
they will
Yes.
give us a better
Result.
result.
Yes.
But I want to know, is there any particular metal ion like we should always use for this? I mean, for a better result, like, is there any difference between using all this iron, zinc, copper? Like, are they into consideration, or do they
Okay.
contribute in the yielding of the result?
Okay. Okay. Um, the result does not just depend on the metal, but the result also depends on the nature of the compound you are using. Now, in my purine, copper is giving me highest results. I might use aspirin now. Maybe I might work with aspirin, and copper might not give me a lower result, while zinc might give a higher result than copper. So it's not only on the side of the metal, but also the metal and the nature of the substrates, the nature of the ligand you are using. Both of them will contribute to having a good result. But meanwhile, we advise to work with the first series transition metal. Yes, we advise you to work with the first series transition metal. At least this first series gives better result because they are lighter. They are lighter than the second series and the third series. Most people use actinides and lanthanides, but this lanthanides and actinides, they are rare earth metals, and then they are heavy. So most times computational models cannot interpret their results. So in summary now, the best that I can say is work with the first series transition metals. Yes, starting from scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. You can work with them. We can work with them, use each of them, and see the one that will give you a better result before going to the lab. I think I've answered the question.
Sure. Thank you.
All right.
And also, uh, does does the target for the drugs also contribute in it? Like maybe if something you want to use to cure malaria, like does the target contribute to the efficacy of?
Yes.
Do you understand the question?
Yes, I do understand you. The target contribute also because this result you see is a binding result, and this binding result was not only the result of the copper, but the result of the copper binding with the target. Now, if you are working with drug, your disease target have different amino acids. A protein, you may not understand, but let me just try my best. Your disease target has molecules. So those molecules in your disease target will bind to your ligand, to your nanoparticle. So the nature of the functional groups in the disease target also has a role to play in the binding interaction. Because if a man and a woman they bind, not be only the man will determine whether they will born pikin. Now both the man and the woman, so depending on how they do the thing for them to feel born pikin. So both you say so both the man and the woman has
I want to ask whether we see the talk the same thing.
Oh yeah. So both the man and the woman has a role to play in the knacking, all right? So, any more question? Should I give you assignment?
We have tried for today.
Should I?
Kill us.
No, sir.
Okay, no assignment.
No, sir. No, sir. Please, thank you.
We don't have the app now. What are we doing again? We know the app.
Okay.
Next time. We don't have the app. I think that we have the app that can help us cover this thing.
All right, see the assignment.
And then, Mr. Henry, please, how can someone get this pirate?
We will come for the advanced training.
Okay, Henry.
We will come for advanced training. I will give you the software.
Okay, it can only be got to come.
There is a way you can get it. I will tell you. That is.
Wow.
Now, until we come for advanced training.
Yes.
Okay, there's the way we can get it. We can get it. It is online.
Now, what is the benefit?
Okay.
What will you get if you get it online?
What assignment are there?
Okay, no. We must still do assignment. Your assignment is this,
Chimo.
Okay, Henry, please.
No, I don't teach that way. I don't teach that way. Anything I teach has assignments.
What's the assignment?
Now, the assignment is...
What's the assignment? Let me see now.
You have already modeled 51 compounds already, right? All of you have 51 compounds you have modeled. Shay? All of you have 51 compounds.
Yes.
Sure.
For each of them.
Yes.
For each of them.
Yes.
I will give you 5 meters. Each of them, you are going to model 5 nanoparticles for each. Is it hard?
Jesus Christ of Nazareth. Each of the
for each of them.
Yes.
Hey.
That is
Okay.
5
5 times.
Okay.
5 times.
Okay, please, will there be a video for this particular section?
Yes, there's a video.
I beg, help us.
Yes, by
Will
the
there be
way,
a video for this section?
yes, there's a
Okay,
video.
because I almost slept.
We have a video for it.
Okay, no while about 5 tips.
Okay.
That assignment,
It's too much.
we
Please
don't finish this year.
limit it.
I beg, the assignment plenty.
But
Ejo,
Okay,
work won't finish us.
okay. Oh yeah,
I
let's.
beg.
I'm still recovering from the last one we did though.
Okay. So what we'll do now, let's use only one meter for all, right?
Ah,
One meter is good now. for all.
finally. But it's still plenty, oh.
No, at least is now less. So I will give each of you the meter you are to use.
It's still
At
plenty.
least we can choose like we can at least use, let's say, 25 meter out of the 50. I mean
No.
25 compound out of the 50
Olo. One meter for
model
all.
distance.
Olo.
Let's use like 25.
Olo. 1 meter for all.
Use-
One person will work with zinc. Another person will work with iron.
Can
Another
we
person will work with copper.
can we combine?
No.
Oga Henry. Oga Henry.
I dey hear you.
No, Oga Henry, I want to ask a question.
Okay,
I want to ask a question. Okay, now in this modeling that you want us to do, like, are we to use different method on it? Like, the first one we duplicated the compound, then fix the meter
Yes.
on it.
Yeah,
Then
duplicate
the
it.
other second one
Duplicate.
we use like the second method. I don't know if you understand what I'm saying.
Yes, I understand you. Do the duplicate. Use the duplicate.
The other one we model it. We model it with the okay, we duplicate it.
Yes, use the duplicate. So this will be part of our project work.
Are we still to go through the rigorous process of minimizing?
Yes, you minimize.
Oga Henry.
Yes, you minimize. You
Can you hear
save.
me?
You do notepad.
Notepad, how are we going to know the name? When it's not showing any name.
You just add zinc.
He said you do zinc.
Zinc of the name.
Those
Zinc.
long names. Okay, just add zinc to it.
Zinc to the name. Zinc to the name. Zinc.
Okay,
to the name.
zinc and then the name.
The name.
Okay.
Yes.
Oh, no wahala. No wahala.
I'm
But
not
there will be no
the
table
last
for this,
video.
right?
I'm not if you play the last video.
Do I even know? I don't even know if I have played it.
It's only ID.
Yeah, I did. I played it.
Okay, how was it? How was it?
It was okay. It was okay. That's why I need this other video too, so that I can use it for the work.
All right, I will drop the link. I will drop the video tonight or latest tomorrow morning, so that you can. Tonight, I will try tonight, so that you can use it and practice. Okay. Please. By we are entering.
Mr. Henry, I still ask, do we need? Can you hear me?
Yeah, go ahead.
Mr. Henry,
Yes, go ahead.
please, I want to know this other assignment that you gave us lately. Are we going to draw any table for it? Because I know we don't have the software to get the information, the data. Are we going to draw any table for it?
No table. You are just getting the structure and send by the solution. So no table.
Okay. Okay. All right. Thank you.
Okay. By next week, by Wednesday, we shall now look at reaction mechanism. So I would like all of you to study on your own. Do a study. We have 15 minutes left. On your own, do a study on reaction mechanism, bond cleavage, homolytic cleavage, heterolytic cleavage, your Friedel-Crafts acylation, Friedel-Crafts acylation, condensation reaction, sulfonation, all those simple reactions. We are going to see how we can do a reaction mechanism by Wednesday. How to show a reaction equation using ChemDraw. Yes. Then, this week would have been the 4th week. Hope you know. Are you aware? Hello?
It would have been.
Yes, it would have been, right?
Yes.
But I will extend
Yes, it would have been the 4th week.
Yes, but I will extend it to next week. So our class will be summarizing by next week, Wednesday. Yes. You won't learn forever.
Okay. Oh, please, what if our assignment is not Wednesday? We're submitting it. Oh.
You are submitting the assignment Wednesday afternoon.
Hope this assignment is not
It's Wednesday afternoon.
I beg. Hey. Ha. Away.
Now you go bed. Now you go first submit.
Ha. Long.
Okay. Now you.
I beg. Oh, my tomorrow day choked up. I've been very choked up.
Let's just see what we can do.
Yeah,
This one is not weekend though.
My name is the week self from Tuesday to Friday. No, they don't cover them.
Chai. Okay.
Okay. Oh.
Okay. Let's just see.
I beg to take my leave because.
Okay. Thank you very much for coming around today. We shall meet on Wednesday.
Leave this thing to next.
Shall meet on Wednesday.
Thank you.
Thank you. God bless you.
Thank you.
Thank you, Henry. Good night. Because the virus is highly.
Rest. Which one is pirate?
I need the app now. I need the app.
This boy want to learn everything. He want to learn everything. It's where.
I swear down.
That is a passion.
Do you know my supervisor was like, what do you mean? You are learning computational chemistry. You are HND.
You are not serious, so who is your supervisor again?
Mr. Gara.
This boy in a chocolate.
It was like, you are learning computational chemistry. You are HND. What do you mean? I said, I have seen it now.
Tell him that
you went to tell him you are doing computational chemistry.
Thank you very much. Good night.
Yes.
Good night.